We're trying to represent the global atmosphere using a grid that looks something like this toy based on the icosahedron. This is an icosahedron. And so we have been working very hard for a number of years on mathematical methods to represent what's going on in the atmosphere by dividing the planet up into little chunks in a way roughly like what's suggested by this picture. So that's one big area, and we're representing not only the atmosphere but the ocean and the land surface this way. The other really big push is clouds, and clouds are very beautiful. A lot of people recognize the beauty of clouds, but they're also very, very complicated and very fascinating. They do a lot of really important things in the atmosphere. And so we have a large project, actually several large projects that are aimed at understanding clouds better, and especially what they do in the global climate system. Well, of course, it varies from case to case, but when a new student arrives, we look for a thesis project that fits with the student's interests, and of course fits with my interests, and also fits with what I'm being funded to do. And since I'm doing global modeling, which covers, everything, it's usually possible to find something that the student is interested in that fits. Now, I should mention that some of my students do dissertation projects or master's thesis projects that are purely or almost purely observational in nature. It's not all modeling, because an essential part of the modeling work is checking the model against data. And so we do quite a bit of work with the observations, and some of the thesis projects are entirely of that type. Some of the students have gone into the field and done things like launch balloons and go on research flights in aircraft and so on. But even the students who do observational work have to do a lot of work with the computer. I mean, computers are not only for simulation. They do arithmetic, and if you're working with atmospheric data, you've got a lot of numbers. And so working with computers is really a pretty essential part of our field today. There's no way around it. The problems we're trying to solve are problems that literally take decades, if not centuries, to solve. They're big problems. So you make progress, you understand something, but the problem is so big that it's not really completed in a lifetime. So your career consists of, making as much headway as you can, trying to find the fast path forward to some new understanding, and you don't really expect to finish it ever. And that's the nature of science.